Hey guys, right now we're going to look at a static torque problem, and hopefully what you're going to find is these are actually really pretty simple as long as you keep very careful track of all the information that you're being provided. In this situation, we have a 70 kilogram diver standing right here on the end of a 35 kilogram board, and we want to calculate the forces that are being exerted from these two supports. The board's 5 meters long and supports are 1.6 meters apart. So I am going to start by labeling all the forces that are acting here. Um, and we want to be very careful to make sure we are considering the point of application, because if we're going to be using torque, we need to know how far the forces are acting relative to the axis of rotation. When I start with the center of mass, I'm just going to label that center of mass for the board, and that is of course downward force of gravity. mg is equal to, the board is 35 kilograms times 9.8 equals 343 newtons. And our diver is 70 kilograms. Be a bit bigger. Not quite drawing at the scale, but it's okay, it's bigger. mg is equal to 70 times 9.8, which is 686 newtons. And that's it for gravity. What about the other forces? I want to think, what are the directions? Now just think about this. If the board were just resting here, I'll use this marker, and not attached in any way, person stands off to the end, they're going to be pushing it down like that. So clearly this force here has got to be pushing upward. I'm going to call that a normal force because, well, it is. And this one here has got to be attached and actually pulling downward. I'm going to label that FD. Oh, we're off the screen. Okay. FD for force downward. Makes sense. And that is pretty much everything. So how will we approach this? If I just try to analyze forces, then I have a problem. I've got three downward forces. Basically, I have two unknowns. So I can't just use a net force equation. I'm going to use a net torque. Now, obviously, the thing is not rotating, so the net torque equals 0. Which means that all of the clockwise torques must equal the counterclockwise torques. I just have to identify what those are. Now, the tricky part here, well, it's not really tricky, but the weird part is we're trying to define an axis of rotation for something that is not rotating. So the fun part with that is you can make it wherever you want it to be. Just decide on a place. So a good approach is to choose a location where there's a force acting that you do not know the value of. So I think I will start with saying my axis of rotation is right here, which means this force has no radial distance from that axis, so it is not exerting a torque, and I can leave that out of the equation. That leaves these three forces. So my clockwise torques, oh well, now I have to define what the radii are. This one, R, is 5 meters. This one is halfway. We're assuming a uniform board. R is 2.5. And this one we're told is 1.6 meters. So now let's see my clockwise torques. Anything that's going to push and make it move clockwise, that would be this one and this one. I've got 2.5 times 343. That's a torque exerted. Jaden, you gotta be quieter. That's the torque exerted by this force. This one would be 5 times 686. And then the counterclockwise torque would be exerted by the normal force, which equals 1.6 times the normal force. And if I solve for all of that, I'll skip the part where I plug that in my calculator, I get 2,680 newtons. So now we found the value for this normal force here is 2,680 newtons. And I need some room here. I'm going to erase this, but you can always go back and look at that part again. So that gave us this force. Now we need to work out this one. And we have two possible options here for an approach to solving that. I could now use an F net equals 0 approach, where all the up forces equal the down forces. So what are my up forces? I've just got normal force equals the downward force here plus mg of the board plus mg of the person. So that's 2680 equals the downward force plus, what did we say? The board was 343 plus 686, and my downward force is equal to 1,651 newtons. So that's a nice simple way to solve that. But just to show you another option, I could have done a net torque equals 0 equation. You're probably thinking, we just did that. That's not going to work for us. But what we can do is change our axis of rotation. So I'm going to move that away and say, for this part, I want this force to be doing something over here, so I'll make this the axis of rotation. Really, it could be anywhere, as long as this force will be part of the equation. What that means, of course, is I'm going to have different values for the radii. This one is now 0.9 meters. This one is 3.4 meters. And this one is, of course, 1.6 meters. So then I could write my clockwise torques equal my counterclockwise torques. Clockwise would be things pushing in this direction. That's this force, RF, is 0.9 times 343 plus RF here is 3.4 times 686 equals my clockwise torque. Sorry, counterclockwise is 1.6 times my FD. And naturally, I'm going to come up with the same answer, because it is the same force.